Okay, so for chapter 12, we are still dealing with fluids, but now we're dealing with fluid dynamics. Chapter 11 was statics, now we're dealing with the dynamics of the fluids. And both of these PowerPoints are in the same file, I believe, on Blackboard. And this one's only, I think, 14 slides. That's why I'm kind of doubling up on these. But just go ahead and follow them through. Um, like I said, there's a lot of chemistry-based equations on these. So you should have seen these maybe a few times before. So the first thing we're going to handle is flow rate. From this graph here, or this figure here, see how we already have area again? We have distance. Here it's distance. Before we were saying it was h, or average depth. And we're dealing with volume, but here for flow rate, which is Q, is the volume of fluid per unit time flowing past a point through the area A. So the flow rate is the fluid actually moving through here, the rate of it. So here, the shaded cylinder of the fluid flows past point P in a uniform pipe in time t. The volume of the cylinder is area times distance, and the average velocity is velocity, which is vector, equals distance over time. So that the flow rate is Q equals A dt, but we know that dt is V. So Q equals AV is our first equation here. So right off the bat, example 12.1. How many cubic meters of blood does a heart pump in a 75-year lifespan, assuming that the average flow rate is 5 liters per minute? So here you go. You have Q equals VT, right? So from right here, this is the equation we just found. And we're just looking for volume. So we're going to multiply the T across. So we have volume equals 5 liters per 1 minute times 75 years, but we know that we have to change the minutes to years. So this is the conversion for it. Again, you can do minutes to hours, hours to days, days to months, and months to years. But this is the direct conversion to it. And we're also changing the 5 liters to meters cubed. Okay. So substituting everything, putting everything in there, you get 2.0 times 10 to the 5th meters cubed. Pretty straightforward to it. You use one equation and you get the answer. So the equation of continuity, when a tube narrows, the same volume occupies a greater length. So you have this longer cylinder type deal here, but now you have this same volume going into a tighter space right here. So see how the cylinder here is wider, but here it's more narrow, but it's longer as well. So for the same volume to pass points 1 and 2 in a given time, the speed must be greater at that point. The process is exactly reversible. If the fluid flows in the opposite direction, its speed will decrease when the tube widens. Note that the relative volumes of the two cylinders and the corresponding velocities vector arrows are not drawn to scale. So don't take these lines seriously. If the fluid is incomprehensible, then we can use the equation of continuity, which says that the flow rate must be the same at all points. So Q1, Q2, so flow rate, and we have our area 1, velocity 1 equals area 2, velocity 2. So the area here of the widened cylinder, and you have velocity 1 times area 2 of this cylinder, the more longer one, and velocity 2. So a nozzle with a radius 0.25 centimeters is attached to a garden hose with the radius of 0.9 centimeters. If the flow rate through the hose and nozzle is 0.5 liters per second, calculate the speed of the water in A in the hose and B in the nozzle. Okay, so first we have to solve for Q for velocity 1. So we have velocity 1 equals Q over A1, but we know that the area of a cylinder is pi r squared. You have to be sure to use the right radius. So here we have 0.5 liters per second, which is the flow rate, times the conversion of it, times pi r squared. The r here is the 9 centimeters, and this gives us 1.96 meters per second for the first one. So for the second one, we do the same thing. We could repeat this calculation to find the speed of v2, but we will use the equation of continuity to give the somewhat different site. So you could use that same equation, this one for v2, but we're going to go ahead and just use a1 v1 equals a2 v2, because they should stay the same, right? q1 should equal q2. So if we do it this way, we know a1 and a2 are areas, so we find the areas for those cylinders. And we also know v1 now that we just found. So substituting the known values, you have 9 centimeters cubed, or squared, over 0.25 centimeters squared, times the 1.96. And this will give us 25.5 meters a second. And that's velocity 2. Now notice here, pi, you don't really have 3.14. They just cancel out. It's the same value, so they cancel out each other. So Bernoulli's equation, probably have ran into it a few times in chemistry or some other class. So when a fluid flows into a narrow channel, its speed increases, as we just saw with the example. That means its kinetic energy also increases. Where does the change in kinetic energy come from? The increased kinetic energy comes from the net work done on the fluid to push it into the channel and the work done on the fluid by the gravitational force, if the fluid changes vertical position. So remember the work energy theorem, 1/2 mv squared minus 1/2 mv naught squared. There is a pressure difference when the channel narrows. The pressure difference results in a net force on the fluid. Recall the pressure times equals the force, times area equals force. The net work done increases the fluid's kinetic energy. As a result, the pressure will drop in a rapidly moving fluid, whether or not the fluid is confined into a tube. There are a number of common examples of pressure dropping in rapidly moving fluids. Shower curtains have a disagreeable habit of bulging in the shower stall when the shower is on. The high velocity stream of water and air creates a region of the lower pressure inside the shower and standard atmospheric pressure on the other side. The pressure difference results in a net force inward, pushing the curtain in. You may also have noticed that when a passing truck on the highway, your car tends to veer towards it. The reason is the exact same. The high velocity of the air between the car and the truck creates a region of low pressure, and the vehicles are pushed together by greater pressure on the outside. This effect was observed as far back as the mid-1800s, when it was found that trains passing in opposite directions tipped precariously toward one another. So here's a figure of a car and a truck, thing we just discussed about. An overhead view of the car passing a truck on the highway. You see how you have velocity 1 here. They're all moving in this direction, but velocity 2 is more narrow here. So the pressures between these two are the initial pressures, or the in pressures, and the pressure on the outside is pushing them inwards. So air passing between vehicles flows in a narrow channel and must increase speed, which is why you have these airways kind of constricting here. V2 is greater than V1, causing the pressure of them to drop. Pi is less than Po. Greater pressure on the outside pushes the car and the truck toward each other. Okay, so Bernoulli's equation again. The relationship between the pressure and the velocity in fluids is described as quantitatively by Bernoulli's equation, named after its discoverer, Daniel Bernoulli. Bernoulli's equation states that for an incompressible frictionless fluid, the following sum is a constant. P equals 1/2 rho v squared plus rho gh equals a constant, where P is the absolute pressure. Remember, the total pressure between the atmospheric pressure and the pressure gauged. Rho is the fluid density, v is the velocity of the fluid, h is the height above the reference point, and g is the acceleration due to gravity. If we follow a small volume of fluid along its path, various quantities in the sum may change, but the total remains constant. Let the subscripts 1 and 2 for any points along the path that bit of fluid flows. Bernoulli's equation becomes P1 plus 1/2 rho V1 squared plus rho GH1 equals P2 plus 1/2 rho V2 squared plus rho GH squared, or GH2. Okay, so for A, the Bernoulli principle explains lift generated by a wing. So anything coming from like an airplane to birds, anything with wings, you see that the airflow goes above and under it, but the pressures are towards it. So for B, cells use the same technique to generate part of their thrust. Kind of the same thing here. The airflow goes a certain direction, but that middle point is where all the pressures kind of go to it. So Torricelli's theorem is a figure 12.8 shows water gushing from a large tube through a dam. So what is the speed as it emerges? Interestingly, if resistance is negligible, the speed is just what it would be if the water fell from a distance h from the surface of the reservoir. The water speed is independent of the size of the opening. So again, we're following this equation here. So we let h equals h1 minus h2. So you plug this in to, for h1 you do h plus h2, and same thing for h2. You eventually get v squared equals v1 squared plus 2gh. That kind of seems very familiar, right? That goes back to kinematics, the original free fall equation. So figure 12.9, we have pressure in the nozzle of this fire hose is less than at the ground level for two reasons. The water has to go uphill, so the water has to go from the fire truck here all the way up here, 10 meters upwards, and the speed increases in the nozzle. In spite of its lowered pressure, the water can exert a large force on anything it strikes by virtue of its kinetic energy. Pressure in the water stream becomes an equal atmospheric pressure once it merges into the air. Okay, so this is example 12.5. They just didn't signify it here. So fire hoses used in major structure fires have inside diameters of 6.4 centimeters. Suppose such a hose carries a flow of 40.0 liters per second, starting at a gauge pressure of 1.62 times 10 to the 6 newtons per meter squared. The hose goes up 10 meters up the ladder to a nozzle having all inside diameter of 3 centimeters. Assuming negligible resistance, what is the pressure in the nozzle? So here we use the Bernoulli equation, because remember, this got to be a constant from the beginning to the end. So we must first find speeds v1 and v2. So we use the flow rate equals a1 v1. So we're trying to find velocity 1. So we divide this by a1. So we have q over a1. And we know q, which is 40 liters per second. And we know a, which is pi times your radius, right? So remember, this is a diameter, 6.4 divided by 2, 3.2. So that'll give us 12.4 meters a second. So similarly, we find V2. All you have to do is the same equation, but for V2. So you would use still 40 liters a second, and you would use 3 centimeters in this case. So this rather large speed is helpful in reaching the fire. So now we take H1 to be 0 because that's at the very bottom. So this equation, this part here cancels out. And we solve for P2. So you have 1/2 times rho V1, V2, right? Because you're moving 1/2 rho V1 over. And you have V2 already over here. And you're solving for P2. So you move that rho GH2 over 2. And so now you have everything you need. You have P1, which is 1.6 times 10 to the 6, plus 1/2, 1,000 of the density. V1, 12.4 squared minus 56.6 squared minus density again times 9.8, which is gravity, times your h, which is 10 meters. And all this equals 0. So this value is a gauge pressure, since the initial pressure was given as the gauge pressure. Thus, the nozzle pressure equals the atmospheric pressure, as is must because the water exits into the atmosphere without changes in its condition. So nothing's really happening once it's coming out of the nozzle. That's why pressure to it is 0. Right? Because it's got to be constant. If it goes in at atmospheric pressure, which we count as absolute pressure, it's going to go out at the same time. So types of flow. Smoke rises, smoke is a gas, or we consider it a gas. Smoke rises smoothly for a while and then begins to form swirls and eddies. The smooth flow is called laminar flow, whereas the swirls and eddies typify turbulent flow. If you watch the smoke, being careful not to breathe on it, you will notice that it rises more rapidly when flowing smoothly than after it becomes turbulent, implying that turbulent possesses more resistance to flow. Right? So anything that floats upwards, it's gonna keep flowing at the same rate unless it's disturbed. So you can kind of go back to Newton's laws and you can apply it in that direction too. So for A and B, we have for A, laminar flow occurs in layers without mixing. So it's just straight flow. Notice that that viscosity causes drag between layers as well as the fixed surface. So for B, we have, turbulence here. So turbulent flow mixes in the fluids. So all this fluid is just kind of coming in and there's mixers and it's like little swirls here. There's more interaction, greater heating, and more resistance than in laminar flow. So laminar flow is smooth, and there's turbulence. Turbulent flow is a little bit crazy. So applying it to what we were just talking about, the flow rate, flow is laminar in a large part of this blood vessel and turbulent in the part narrowed by the plaque, where velocity is high. So here we have V1 is coming in undisturbed, but once it starts narrowing, it turns into V2 here and then V3 here. So see how the flow starts kind of bending this way, and then once it gets into V3, it starts swirling. In the transition region, the flow can oscillate chaotically between laminar and turbulent flow, which is this is the transition period. So for figure 12.18, for A, we have motion of the sphere to the right is equivalent to flow to the left. Here the flow is laminar with NR less than 1, which is just the, I guess the difference between them. There is a force called viscous drag, FV, to the left on the ball due to the fluid's viscosity. For B, at a higher speed, the flow becomes more turbulent, creating a wake starting where the flow lines separate from the surface. Because in the wake is less than in front of the sphere. Pressure is in the wake and less than in front of the sphere because fluid speed is less, creating a net force to the left FV that is significantly greater than laminar flow. Here NR is greater than 10. And then for C, now you see all this turbulence, right? At much higher speeds, where NR is greater than 10 to the 6th, flow becomes more turbulent everywhere on the surface and behind the sphere. Drag increases dramatically. So the more movement there is, the crazier it got from A to B to C. Okay, and that's really all there is to know about chapter 12. Like I said, it's a pretty short chapter. The homework for chapter 12 is already up, so make sure you are working on that. Same with chapter 11.